So we're talking about the area problem. So what is the definition of area? It's pretty simple to find using simple geometrical shapes such as square or rectangle, just length times width. But say you had like a curve or something more difficult to find the area of. We have to employ slightly different methods for that.
Imagine you are faced with the graph y equals f of x. When asked to find the area of the region S that lies under the curve y equals f of x, on the interval from A to B, we are trying to calculate this shaded region. In trying to find the exact area, we must begin by using approximations. We will first approximate the region S by using rectangles, since drawing their areas is an easy operation that we are familiar with. Let's do an example, y equals x squared. Our goal is to find the area under the curve over the interval 0 to 5. Let's start with 5 rectangles. We divide S into 5 sections, and each section will be a rectangle. Each rectangle then has a width of 1 and a height of f of x. Using rectangles in this way will allow us to find both an overestimate and an underestimate. Let's first use right endpoints, as we have shown here. We will start by taking the area of each successive rectangle. The first one has a width of 1 and a height of f of 1, which, when plugged into the equation y equals x squared, is 1. So the area of the first rectangle is 1. Then we will add this to the area of the second rectangle, which also has a width of 1 and a height of f of 2, which would be 4. Plus 1 times f of 3, plus 1 times f of 4, plus 1 times f of 5. Solving this equation gives us 55. However, this is an overestimate because you can see the area above the curve of each rectangle that we included in our approximation. Let's try this using left endpoints. To do it using left endpoints, we're going to draw our curve again and take the left endpoints instead of the right endpoints. Using a similar tactic, we can find an underestimation of the area under the curve. So since the widths of each rectangle are 1, we can start with 1 and add in each height. So it would be f of 0 plus f of 1 plus f of 2 plus f of 3 plus f of 4. This gives us an underestimation of 30. As you can see, the difference between our overestimation and our underestimation is very large, and so maybe to get a more exact estimation of the area, we can use more rectangles. If we broke it up using more rectangles, we could calculate a more accurate estimation. This applet gives us a graphic representation of what we just talked about on paper. So you can see this is the parabola, f of x equals x squared, with 5 rectangles. And as we had calculated, the left-hand area is 30 and the right-hand area is 55. Now let's see what would happen if we increase the number of rectangles to 10. As you can see, the approximation over the curve is less, so we'll get a better approximation. And indeed, we have a left-hand area of 35 and a right-hand area of 48. what if we put it into 100 rectangles? Now we have a left-hand area of 41 and a right-hand area of 42. These are getting closer together. So let's take it one more step forward and say 1,000 rectangles. And as you can see, the left-hand area is 41.6 and the right-hand area is 41.7. So you can see as n, or the number of rectangles, approaches infinity, the left-hand area begins to approach the right-hand area. And in this case, the area is equal to around 41.6. Here's an applet that will calculate the number of rectangles that we put in and what the underestimate and overestimates are. So as you can see, this is what we did earlier with 5. If we bump it up to 10 rectangles, it's a more accurate estimate, and the left points are 35.6 and the right point.
So let's talk in more general terms about this region S, this area that we're trying to define. The width of the interval from A to B is B minus A. So the width of each rectangle that we're trying to use is B minus A over N. In our first example, when we had from 0 to 5, when we used 5 rectangles, N was 5, so we knew that we had the interval was 5, and we were using 5 rectangles, therefore the width of each rectangle was 1. So now we can essentially say that this was the width, or delta x. So in general, we can say that the first term, or the first right endpoint of the subintervals can be expressed like this: x1 equals a plus delta x. But as we keep going and keep finding more right endpoints, we will have to keep adding on another delta x, another width, and so on. And then for the ith term, depending on how many rectangles we have, we will end up with x sub I equals a plus I delta x. So we have this x sub I term, and if we multiply, or if we input this as the x value for our function, so f of x sub I, and we multiply this by delta x, so this will be essentially acting as the height of the right endpoint. This will be the width, delta x. If we multiply these two together, we should get the area of one rectangle. But if we sum all of these rectangles, and in this summation notation, or sigma notation, we can specify that we want to go from I equals 1, so the first term, all the way until the nth term, and sum all of these rectangle areas. We should come up with the area, all the areas of the rectangles. So this only works for a defined number of n rectangles. However, we know from previous examples that as we get larger in number of rectangles, we will get more accurate in our estimation of the area. So why don't we say that n is tending towards infinity, or the limit as n goes to infinity of all of this should equal the real area under that rectangle. And this is, in fact, how we derive the area under the curve. So, to conclude, we have the area of A, of the region that we called S earlier, that lies under the graph of the continuous function f, we have set that equal to the limit as n goes to infinity of the sum from I equals n of the areas of rectangles, or basically f of x sub I times delta x, the height times the width. Thank you for watching!
Wow, using those skills, you can now find the area under any curve. See you next time!
Bye.